Okay, so precipitation. I mentioned before that my favourite satellite is this Global Precipitation Mission satellite called GPM. It's a core observatory of a constellation of satellites devoted to measuring rainfall across the globe. This one in particular is my favourite because it's revolutionised the way we do space-based rainfall estimation. On board this platform, orbiting at about 750 kilometres above the Earth, is a weather radar. So like the same technology that you'll go to the Bureau website and see if it's going to rain today or not is based in space on this platform, along with other technology in the microwave region of the electromagnetic spectrum. The conversion of the signals it measures into a rainfall amount in and of itself is a beautiful thing, and I could gush for hours about it, but I'll shut up now and move on. But I love it so much that I even made my own Lego version of the thing, and I think I did a pretty good job. So yeah, GPM is a integrated multi-source retrieval of rainfall estimation across the globe. It uses a constellation of satellites, so many satellites measuring similar things to GPM, and where the overlaps occur, that's where they get the signals calibrated. Offers you global coverage, and every half an hour for the whole globe, you get rainfall estimation at about 10-kilometre resolution, which is unparalleled for space-based estimation. So we set about a few years ago to try to see if we can use the predecessor of GPM called TRMM, to fill in the gaps between the radar, the gauge network, to provide real-time rainfall estimation for Australia. And our research took the real-time gauge network, which, as I mentioned before, it looks impressive perhaps at this scale, but as you zoom in, you see that many parts of the country have either zero, very few gauges per 100 kilometre by 100 kilometre cells. And when you think of the vastness between these gauges, you do have to question some of the rainfall estimates we get from, say, the Bureau of Meteorology. On the bottom right here is what they call the gridded analysis. Whenever I mention analysis, interpret that as the best estimate that can be made. So the gauge-based analysis is given here for the real-time rainfall. And you can see that there's just some parts of the country you can't trust the estimates because there's just no gauges for thousands of kilometres. So take these gridded rain gauge analyses with a pinch of salt. They're not perfect, but where you've got gauges, they're pretty good. So we asked the question of whether or not we can do a better job filling in the gaps between the network. So we set about looking at various algorithms. My colleagues and I developed a few methods of merging the gauge network with the satellite network, this precursor to GPM called TRIM, and explored various methods of co-kriging, called a method my mathematician colleagues came up with, some other sophisticated methods, and evaluated them against the independent set of gauge networks around the country, and showed that there was some success in this approach of merging gauges and satellite data. So that was very promising and encouraging. So then we thought we'd extend the idea a bit further, then rather than just merging satellite product, which we know has problems. Remember earlier on I said you've got two satellite systems measuring rainfall over India. They don't always agree on the extent of the rainfall, let alone the absolute amounts of rain that fell. So satellite data are flawed. The alternative is that use model data, so stuff that comes out of weather forecast models, NWP models they're called. Australia's NWP model is called ACCESS. So we can get ACCESS estimates of rainfall, but they're model estimates. They don't actually use the rain gauge data to improve the models and estimated rainfall. And of course, you've got the radar network as well, which is gappy. So we asked that same question, is there a way of combining all these sources of rainfall information to get a better estimate overall for Australia? Why do you want to merge? Well, it fills in the gaps, it improves the accuracy, and what you try to do is inherit the good properties of each one of the input data sets and ignore and mitigate the deficiencies in their respective data sets too. So we came up with methods and we applied it to test areas around Australia and found you could actually do a reasonably good job. So we're quite pleased with this idea of merging radar, numerical weather prediction, and satellite estimates of rain to get that seamless coverage across the country in real time. So this is work that my colleagues and I at the Bureau of Meteorology are developing for the country. Yeah, just to illustrate that point again, the radar network by itself has limited coverage. We fill in the gaps with the satellite data through methods of statistical blending of the data and generally get satellite data and the NWP data, and we get a better estimate overall. So we learned a fair bit from this exercise, not least of all that no single rainfall information source has all the characteristics we want. You might have the resolution, but it's got poor coverage. You might have the timeliness, but the accuracy is pretty poor. But for some communities, they would trust nothing but rain gauge data, despite the fact there's vast kilometres between gauges that prefer to get an interpolated value. Merging is a way of increasing the utility of data sets by combining the strengths of the input sources of rainfall and mitigating their respective deficiencies. It improves the accuracy as well, we've seen. Real-time aspects. So, you know, for severe weather, knowing what's happening now is paramount. So most emergency services require extreme estimates of the ballpark. Is it going to be devastating? Is it going to be moderate? You know, so ballpark figure stuff. But many hydrological modelling communities prefer waiting a little bit so the quality of the estimation can be improved. Because what we try to do in real time is collect as much information as we can, understanding that it's probably not the most complete information, but it has that low latency, that we don't have to wait, the low delay in getting the data. One thing I haven't mentioned here is that because you're using multiple sources of rainfall information, and if you believe that they can represent the spatial patterns of rainfall adequately, you can construct what's called an ensemble. And an ensemble is a way of explicitly characterizing the uncertainty in the rainfall estimation. So rather than saying it's going to be 10 millimeters of rainfall falling in the next hour, you can say it's going to be 10 with a confidence of 80%. But that's always hard to convey that kind of statistic to members of the public. So understanding ensembles and then interpreting them or getting relaying or conveying that information in a way that's accessible to members of the public is a challenge.